Welcome to this explainer. We are diving straight into something that hits literally every technical team automating workflows eventually, building a Captcha solving queue in Node.js. It always starts the exact same way. You've got a system, it's firing off requests, and suddenly, bam, you have way too many Captcha-related tasks just sitting there waiting on external API responses. It seems like a simple problem at first, right? But if you don't handle it, it quickly turns into a massive operational bottleneck. Now, initially, the fix feels super obvious. You just submit the tasks in parallel, wait for the results, retry whatever fails, generate your tokens, and move on. And honestly, for a tiny batch of tasks, that probably works just fine. Node.js is naturally single-threaded, but it is an absolute beast when it comes to I/O concurrency. So teams usually just throw together a quick promise-all-settled approach. It runs a few tasks, tells you what passed and what failed, and you call it a day. But when that workflow scales up and hits real heavy-duty production traffic, it completely falls apart. This is where we need a total paradigm shift. You have to completely rethink the problem. The question isn't, can Node.js physically run these requests concurrently? We already know it can. The much better, much more mature question to ask is, can our team actually control the throughput? Can we prioritize the critical tasks, recover smoothly from failures, and actually monitor this queue before it turns into a nightmare? See, a properly built Captcha-solving queue isn't just a Node.js coding pattern. It's an actual reliability system, one that protects your most critical workflows. So how do we actually build this reliability system? Well, based on our source material, we're going to walk through an 8-step practical queue checklist. Think of this as your essential operational playbook. Because, and consider this a fair warning, a poorly designed queue doesn't usually crash loudly. Instead, it just quietly drains your system, creating massive hidden delays, skyrocketing API costs, and silent rate limit throttling. So let's make sure you avoid all of that. All right, step 1 of the playbook, defining your workflow priority. You really need to step back and ask which tasks are genuinely business critical here. Which ones are just background jobs and which ones can literally just wait? Say you have a customer-facing checkout flow or maybe an immediate release gate. Under no circumstances should those be stuck in line behind a giant batch of low-priority data scraping jobs. Your queue's priority has to reflect the actual business impact, not just the random order tasks happen to arrive in. Moving on to step 2, which is all about setting concurrency limits. Start with 5 to 10 concurrent solves. That is a solid conservative baseline. Like we said, Node.js handles I/O concurrency like a champ, but that absolutely doesn't mean you should run every single task at the exact same time. Do that, and you'll immediately trigger failures because you're eating up unavailable slots with too many concurrent API calls. Start small with 5 to 10, and then safely adjust that number based on your success rate, your average solve time, and your specific provider limits. Step 3 brings us to a massively important concept, backpressure. Look, if tasks are piling up faster than your system can finish them, your queue is going to grow. Backpressure is simply the set of rules deciding what happens when that queue is totally full. Do new tasks wait? Do we reject them outright, delay them, or maybe bump them to a lower priority? If you skip setting up backpressure rules, your memory usage will just balloon endlessly, and your entire Node.js system will eventually become completely unstable. Step 4 is super straightforward, but you'd be surprised how often it gets missed. Separate your task types. A small background batch process and a real-time user-facing workflow are two completely different beasts. They should never be dumped into the same queue with the exact same rules. Different task types naturally need different priorities, completely different timeout rules, and their own unique escalation paths. Okay, step 5. We have to design our retry logic very, very carefully. Retried failed tasks is obviously necessary, but careless retries, those are incredibly dangerous. If you just blindly retry everything, you create what's called a retry storm. If a task fails because of a bad parameter or a permanent setup issue, retrying it 100 times just burns through your API quota and costs you money. Instead, you want to retry transient failures only, strictly limit your attempts, add delays between submissions, classify the error types, and most importantly, move those persistent, unfixable failures out of the main flow and into a dead letter queue. Step 6 is all about visibility. A queue without monitoring is literally just a black box. By the time someone notices a delay, your system could be thousands of tasks in the hole. You absolutely have to track core metrics. You need to see submitted and active tasks so you understand your current load. You've got to monitor average solve time and success rate to gauge actual performance. And tracking that dead letter count we just talked about, that is the only way you'll catch persistent systemic errors before they blow up into a full-on crisis.
Building right off that visibility is step 7, establishing escalation rules. It's great to have a fancy dashboard, but you need to define exactly when a human being actually gets pinged. You need hard alerts for when the success rate suddenly tanks, when the dead letter volume spikes out of nowhere, or when high-priority tasks are just sitting there waiting way too long. These alerts are your safety net. They give your team the power to jump in and fix things before the downstream workflows completely fail.
Which brings us to the final step of our checklist. Step 8 asks one critical question: who actually owns the queue configuration? I mean, who is in charge of the max concurrency setting? Who tunes the rules, reviews those dead letter items, and keeps an eye on the provider limits? The bottom line here is this: if nobody explicitly owns these decisions, your shiny new queue rapidly turns into operational debt. Someone on the team has to officially own it. Now let's move into our section on common mistakes, specifically looking at what quietly ruins Captcha queues. Let's run through these quickly because they act as a fantastic summary of exactly what not to do. Mistake 1, running too many solves at once. The consequence? Bam, every single promise rejects simultaneously because you just hit an API rate limit. Mistake 2, treating every task as equally important. The result? Your critical checkout flows get entirely blocked by routine background jobs. Mistake 3, retrying bad requests forever. That just clogs your dead letter queue and drives up your API costs for literally no reason. And mistake 4, tracking only the completed tasks. This gives you a totally false sense of security while completely hiding your actual queue depth and system latency. Before we wrap things up, we need to cover a very strong, very necessary disclaimer. When you're building automated workflows that use Captcha solving, you have to be rigorous about compliance. This absolutely requires checking permissions, platform rules, and your contractual terms. These systems are incredibly powerful, but they should only ever be built and operated in owned, client-authorized, or contractually permitted environments. Always, always respect the operational risk and the legal boundaries of the platforms you're interacting with. Finally, let's jump into a quick FAQ covering final operational tuning. All right, first common question: exactly how many concurrent solves should a team run? Like we talked about in the playbook, the golden rule is to start conservatively. Stick to that 5 to 10 range at first. You really don't want to blast the API right out of the gate. From there, just watch your success rate, keep an eye on your average solve times, and watch out for any throttling signals from your provider. Once you've got a solid read on your baseline, then you can safely scale up to match whatever limits your provider plan allows. And our last question: when should teams actually use a priority queue? The answer is anytime you have tasks that are more business critical than others. Honestly, it's that simple. If you have a real customer waiting on a screen or a QA release gate that needs immediate clearance, those tasks simply must jump to the front of the line, way ahead of any bulk background jobs. Priority queues are literally the difference between a frustrating user experience and a completely seamless one. So I want to leave you with this thought to mull over for your own projects. Take a hard look at your current automated workflows. Are you just throwing tasks into a giant single pile and hoping for the best, or are you actually controlling your system's reliability? Think about it. Thanks for joining me on this explainer, and I will see you next time.